Welcome back, everyone. This is Professor Herring. In this video, we're going to do some extra practice problems from the first half of Chapter 16. Let's begin. So, go ahead and pause the video, read through this one on your own, and see if you can solve it, and then watch the video for the solution. Welcome back. So we're given a thermochemical equation for the combustion of methane. We want to know which statement is not true. So let's evaluate these line by line. Enthalpy decreases as reactants are converted to products. Well, if we do an energy diagram here and we look at enthalpy, let's just arbitrarily assign our reactants to be here. And we're given that the enthalpy of the reaction is negative, which means that our products need to be lower in enthalpy. So this is going to be true. The products have higher enthalpy than the reactants. This must be false, as we just shown. The products are actually lower in enthalpy. The reaction releases heat. This is true. When you look at enthalpy of reaction being negative, we know that that's going to release heat. The heat released by this reaction is proportional to the amount of material consumed. This is going to be true. And we discussed earlier how enthalpies of reaction are extensive properties. So it depends on how much you have. And then finally, it's exothermic. Yes, by definition, when its enthalpy is released, it's exothermic. So this one was a little bit of a simple one, hopefully. Let's try a mathematical problem here. Pause the video and try this one on your own before watching the solution. Welcome back. So we want to know how many grams of propane would be needed to burn in order to produce 100 liters of carbon dioxide at 21 degrees Celsius. You should be able to come up with a balanced chemical equation on your own. And then we know that we want to produce 100 liters of CO2. It's going to be a gas. It's 1 atmosphere, 21 degrees Celsius. So we want to know what mass is needed. We're going to need to use the molar mass of methane, which is 44.1 grams per mole. And we're going to need to convert using the ideal gas law to get to moles here. And that's 1 atmosphere, 100 liters, 0.08206 liter atmospheres per mole Kelvin, and then 21 plus 273.15 Kelvin. That's going to be equal to 4.1429 moles of CO2. Which means when we use the stoichiometry, that's going to be equal to the 4.1429 moles of CO2, and then accounting for the ratio of 3 CO2 for every 1 propane, which is 1.381 moles. To find the mass of propane, we need to use the molar mass. And that's going to be equal to 61 grams. If you got through this and wondered, Professor Herring, didn't we do this one already? I think the answer is yes, but I showed it to you again. All right, this is going to walk through a couple digital things here. Blah, blah, blah. It's all the same stuff that we just did. Okay. All right, now try this one. I am fairly sure we haven't done this one before. So pause the video, read through it, and try and do it on your own. Welcome back. Okay, so we've got some barium hydroxide mixed with hydrochloric acid. You should recognize that as an acid-base type reaction. and therefore we would get the following chemical reaction. We're told that there's a temperature increase. We want to know how much, what's the enthalpy of reaction in kilojoules per mole for hydrochloric acid. We're given the total mass of 102 grams and the specific heat. So, how do we do this? We need to first determine the limiting reactant. Okay, so we're going to find the moles of each reactant. We do that by taking and multiplying the molarity times the volume in liters. And then we want to find the limiting reagent. So we can do that by saying how much water do they produce, or how much barium chloride, or how much of the other reactant would be used. In this case, I'm going to show you how to do it for water. So we take the moles of each reactant, convert to water, and then compare. This is going to be our limiting reactant because it has the smaller amount that's produced. Since the barium hydroxide is the limiting reactant, we can't just use the amount of hydrochloric acid and use the moles of that. We need to find out how many moles of hydrochloric acid was actually used up. So to do that, we take the moles of barium hydroxide that we used, multiply by the stoichiometric ratio, and this is how much hydrochloric acid is used. This is going to be our N in terms of Q equals N delta H, or rearranging H equals Q over N. Okay? So now we need to find Q of the system. To do that, we're going to start by calculating the Q of the surroundings and set that equal to the negative Q of the system. We're going to need the specific heat, the mass, which we're told is 102 grams, and the temperature change. That gets us just under 2,000 joules, or under 2 kilojoules. Take the negative of that, again, because we need to, when we're talking about the enthalpy of the reaction, that's going to be the Q of the system. So take the negative of that, and then divide by the moles of hydrochloric acid that's used up. Again, not the total moles of hydrochloric acid, but the amount that's used. And that gets us then negative 56 kilojoules per mole. Okay? Why don't you try another one? Pause the video and try this on your own. Welcome back. So in this case, we have an unknown salt dissolving it in water inside of a coffee cup calorimeter. The temperature decreased by 10 when 1/10 mole of the substance was dissolved. What's the heat of solution per mole of this substance? So the heat of the solution we know is the Q of the system over the moles. We're told that it's 0.1 molar, or 0.1 moles, and so we need to find Q of the system. Q of the system is equal to negative Q of the surroundings. And Q of the surroundings is equal to the specific heat times the mass and the temperature change. So our specific heat is 4.184 joules per gram degree Kelvin, and 10 grams, and then a change of 10 degrees. And it's decreased, therefore it's going to be negative 10. That's equal to negative 418.4 joules. Set that equal to negative to solve for the Q of the system, and then divide by the number of moles to find the enthalpy of the solution. Convert to kilojoules, and we see that that's equal to 4.2 kilojoules per mole. All right, one last problem. Go ahead and try this on your own before watching through the solution. Welcome back. So you're given some reactions here, and you're wanting to find the heat of the reaction. This is going to apply Hess's law. Hess's law allows us to multiply by a factor or to rearrange the equations in order to get the desired reaction. So my recommendation is, let's label these as reaction 1, reaction 2. And to start by identifying one of the substances in the final reaction that only shows up once in the reactions above. So here we've got sulfur dioxide gas. It's in reaction 1 right here. And we have the correct amount, but it's on the wrong side of the equation. So we need to multiply this whole equation by -1. Then, oxygen. Well, we've already accounted for oxygen in the reaction above. Now let's look at the next one, water. Water shows up in the second reaction. It's on the proper side of the reaction, but the wrong amount. We need to multiply by a factor of 2. So if we rewrite these equations, we're going to get 2 sulfur dioxide gas plus oxygen gas yields 2 sulfur trioxide gas, and 2 sulfur trioxide gas plus 2 water liquid yields 2 hydrogen sulfide liquid. If we add these together, we get 2 sulfur dioxide gas plus oxygen gas plus 2 sulfur trioxide gas plus 2 water liquid yields 2 sulfur trioxide gas plus 2 hydrogen sulfate liquid. Cancel any like terms, which is we've got 2 sulfur trioxide gases, and then everything else looks like it follows through. If we rewrite that, we have 2 sulfur dioxide gas plus oxygen gas plus 2 liquid water yields 2 H2SO4 liquid. Now, we don't want to just stop there. We want to make sure that that matches. 2 sulfur dioxide, check. 1 oxygen, check. 2 water, check. 2 H2SO4, check. So we know we've done that right, which means then that we can take our first enthalpy of reaction and take the negative of that plus 2 times the second enthalpy of reaction. That's going to then be negative 196.7 kilojoules plus 2 times negative 130.1 kilojoules. Add that together and you get negative 456.9 kilojoules. Okay, that's it for this video. Thanks for watching. If you have any questions, you can ask on Piazza, in office hours, or recitation. See you later.